Welcome to this technical case study presentation on Gearbox failure analysis. This engineering case study is presented by IndustrialHub BD, Plant Reliability Partner. In this presentation, we will analyze the root causes of a catastrophic gearbox failure in a steel manufacturing plant and discuss how predictive maintenance can prevent such failures. First, we see the whole study in a glance 1, executive summary 2, equipment background 3, problem description 4, inspection and diagnostic process 5, engineering analysis 6, corrective and preventive action 7, lessons learned. First, executive summary. A catastrophic failure occurred in the main reduction gearbox of a steel plant. This failure caused 36 hours of unplanned production downtime. The estimated financial impact was approximately 70 million taka. The failure originated from progressive gear tooth surface damage, which later developed into severe spalling and secondary bearing damage. Early warning indicators were present, but they were not interpreted correctly in time. Equipment background. The failed equipment was a triple reduction helical gearbox. The gearbox power rating was 1,600 kilowatts. The input shaft speed was 1,500 revolutions per minute, and the output speed was 470 revolutions per minute. This gearbox was used in a hot metal reduction process operating in a harsh industrial environment with high vibration and shock loads. Next, operating environment. The gearbox was operating in a challenging environment. Ambient temperatures ranged between 30 to 45 degrees Celsius. The system experienced heavy shock loads during billet biting. Additionally, the surrounding industrial atmosphere contained contaminants that could affect lubrication systems. Observed symptoms. Several warning signs appeared before the failure. Maintenance personnel observed increasing vibration levels near the load zone. An abnormal whining noise occurred during peak load conditions. The gearbox temperature increased from 45 degrees Celsius to 82 degrees Celsius. Metallic particles were also found in the magnetic drain line. Vibration monitoring. Vibration monitoring data showed a gradual increase in vibration levels across the gearbox shafts. The input shaft, intermediate shaft, and output shaft all experienced rising vibration amplitudes. This was an early indicator of developing mechanical faults in the gearbox. Temperature monitoring. Temperature monitoring also revealed abnormal trends. Over several weeks, the gearbox temperature gradually increased. The temperature eventually reached critical levels close to the danger zone. Such temperature rise usually indicates friction, lubrication problems, or internal mechanical damage. Next, failure timeline. The failure developed progressively. During the first week, increased vibration levels were detected. Metal chips were discovered in the lubricant return line. Abnormal noise also became noticeable. Eventually, severe vibration spikes triggered an emergency shutdown. Vibration analysis. During diagnostic investigation, engineers analyzed the vibration spectrum. One of the most important indicators was the gear mesh frequency, also known as GMF. The gear mesh frequency is calculated using the number of gear teeth and rotational speed. GMF equals N times RPM 60. This frequency appears prominently in vibration spectrum analysis when gear problems exist. How to impact GMF spectrum. In vibration spectrum analysis, gear problems appear as peaks at the gear mesh frequency. Sidebands often appear around the GMF. These sidebands are located at GMF plus or minus shaft rotational speed. The presence of sidebands indicates gear wear, load modulation, or tooth damage. The analysis confirmed progressive gear tooth surface deterioration. Oil analysis results. Laboratory oil analysis provided further evidence. The lubricant contained more than 300 parts per million of iron particles. Cutting wear particles were also detected. Lubricant viscosity dropped from ISOVG 320 to approximately ISOVG 290 equivalent. This indicated severe contamination and lubrication degradation. Next, tooth contact pattern test. A Prussian blue tooth contact test was performed. The inspection revealed that contact was concentrated near the heel region of the gear teeth. The contact band covered only 35% of the face width. Ideally, the contact pattern should cover 60 to 70% of the gear face width. This uneven contact caused edge loading. Backlash measurement. Backlash measurement revealed another critical problem. The measured backlash was 0.75 millimeters. However, the OEM recommended backlash range was 0.30 to 0.40 millimeters. Excessive backlash caused impact loading and uneven stress distribution across gear teeth. Next, root cause analysis. The primary failure mechanism was surface fatigue on the gear teeth. The damage progressed from pitting to severe spalling. Eventually, load concentration caused secondary bearing damage. Contributing factors included improper backlash, shaft misalignment, lubricant contamination, and lack of structured monitoring. Engineering analysis. Misalignment caused uneven load distribution across the gear tooth width. This resulted in high, localized Hertzian contact stress. The lubrication film became thinner, which led to metal-to-metal contact. These conditions accelerated fatigue and gear tooth failure. Visual inspection. After disassembly, several physical damages were observed. Large spalled areas were present on the gear flank. There were discoloration marks caused by overheating. Bearing race surfaces were worn. Metallic debris was also accumulated inside the gearbox sump. Next, corrective actions. Several corrective actions were implemented immediately. The gearbox was shut down, and the lubricant was drained and filtered. Damaged gears and bearings were replaced. Backlash was reset to the OEM recommended value of 0.35 millimeters. Precision laser alignment was also performed. Monitoring improvements. Monitoring systems were upgraded to prevent future failures. Online vibration sensors were installed. Oil sampling ports were added. Temperature sensors were recalibrated. These improvements allow early detection of mechanical problems. Preventive maintenance plan. A structured preventive maintenance program was introduced. Daily checks were implemented for lubrication return lines. Weekly vibration monitoring became mandatory. Oil flow inspections were scheduled every 3 months. Gear teeth inspection was scheduled every 6 months. Oil analysis and bearing inspection were planned annually. Lessons learned from this case study. Several important lessons were learned from this failure. Backlash control is critical in heavy load applications. Vibration sidebands must never be ignored. Lubrication contamination accelerates fatigue failure dramatically. Reactive maintenance costs 5 to 10 times more than predictive maintenance. Conclusion. This gearbox failure was primarily caused by improper backlash adjustment, shaft misalignment, and lubrication contamination. These issues created uneven load distribution and progressive gear damage. Early warning indicators were present, but were not addressed in time. This case clearly demonstrates the importance of predictive maintenance and condition monitoring. IndustrialHub BD mission. IndustrialHub BD helps industries reduce breakdowns, improve equipment reliability, and maximize plant productivity. We support manufacturing plants through practical engineering knowledge, industrial solutions, and reliability improvement strategies. IndustrialHub BD services. IndustrialHub BD provides industrial systems, spare parts, and engineering solutions. We also support condition monitoring best practices and share real industrial failure case studies. Our goal is to help plant engineers maintain reliable and efficient production systems. Reliability tools. IndustrialHub BD supplies professional reliability engineering tools, including vibration analyzers, laser alignment kits, infrared thermometers, dial gauges with accessories, Prussian blue inspection materials. These tools help engineers detect faults early and maintain equipment reliability. How to contact IndustrialHub BD. For industrial reliability support and technical consultation, please contact IndustrialHub BD, phone +8801 746 881144. Email sales@industrialhubbd.com. Website www.industrialhubbd.com. You can also follow IndustrialHub BD on LinkedIn and YouTube for more engineering case studies.